Hi guys, let's start today by looking at your final exam review. We'll look at this a little bit each day until we get to the final exam. The part of the review that I want to look at though today is the part over our current unit, over chapter 6. So 1, 2, 3, 4, 5. Turn to the 5th page. Take a moment, turn to the 5th page. At the top, it should say Unit 6, Applying Quadrilateral Properties. So in a little bit, I'm going to do an example that looks like this figure here in question 6.1 and question 6.2. This is not as fancy of a question as it looks like. This is simply a way to organize your information so you can make better decisions. It's a graphic organizer. So let's circle the ones that I want you to try for tomorrow. I'm going to ask you to try 6.1 and 6.2. Again, I'll show you examples of those in a little bit. So I'd like to do 6.3 right now. So I want to organize the quadrilaterals that we've studied. So quadrilaterals are four-sided figures. If we have figures where both pairs of opposite sides are parallel, the most basic figure where both pairs of opposite sides are parallel, that's a parallelogram. So, and parallelograms have four basic properties that we've studied. The opposite sides are congruent, the opposite angles are congruent, the consecutive angles are supplementary, and the diagonals bisect each other. So there are two then special kinds of parallelograms. There are rectangles. So rectangles have four right angles. Then there are also rhombi. I'll just write rhombus. Rhombi have four congruent sides. Now, they have their own unique properties. So rectangles have diagonals that are congruent, and you get four isosceles triangles. In rhombi, you have diagonals that are perpendicular, and you have four congruent triangles within the figure. And then rectangles and rhombi together, four right angles, four congruent sides. Of course, you know that gives you a square. And a square inherits all of the properties of parallelograms and rectangles and rhombi. So on your homework assignment for today, I was asking you to think about the following. Exactly one pair of opposite sides are parallel. That's what we call a trapezoid. But then there's one special kind of a trapezoid, that is the isosceles trapezoid. So on your handout for today, your goal was to see if you could figure out what the trapezoid's basic properties looked like. And then on the back side, there were two proofs that involved isosceles trapezoids. I am not going to ask you to do proofs in the future that are as complicated as the two that were on your practice assignment, but they are related to proofs that you're going to see on your final exam. So this is actually a good day to talk about the important characteristics in these proofs that I want you to know and practice going forward. So bear with me while we have the final exam review here. Let me show you what I want you to try again for tomorrow. I want you to try 6.1, 6.2, and then we've basically done 6.3. We'll finish it tomorrow. So if you turn the page, you'll see the practice proofs. For tomorrow, I don't want you to worry about doing proof number 1, P1, and P2. So the ones that I want you to try are review proofs. They are proof 3 and proof 4. So these proofs involve using alternate interior and alternate exterior and corresponding angles and the fact that you have parallel lines in order to show that angle pairs are congruent. And there are many ways to do both of these two proofs. So the other two proofs I want you to try are on the back page. They're P5 and P6. So proof number 5 and proof number 6, what makes these special is these are about making congruent parts. And in order to make those congruent parts, first you have to have congruent triangles. So let's switch now and take a look at the homework assignment for today. That was the study guide trapezoids. So if you don't have one, or if you still need one, you can get one from the folder in the front of the room. Let me give you a moment in order to take this out, and then we'll go over the basic ideas here. I'm just pausing so you can get your stuff out. So a quadrilateral is a trapezoid if exactly one pair of opposite sides are parallel. Again, that's what we had in your final exam study guide, right here in question 6.3. Exactly one pair of opposite sides parallel, that gives you a trapezoid. So here's a trapezoid. The bases are the parallel sides. So these are both parallel because they're horizontal line segments. So PQ and TR, those are the parallel sides. Those are called the bases. What I wanted you to see then is that the same side interior angles here, like P and T, Q and R, those have to be supplementary. So if angle P is 110, then angle T is 70, so those add up to 180. If angle R is 41, then angle Q is 139, so that they add up to 180. So I assume that you can label coordinates. P's coordinates are -1, 5. T, this vertex, is at -3, -1. And what I wanted you to find was the midpoint of that side of the trapezoid PT. So to find a midpoint, all you do is average the x and y coordinates, and that's what I was trying to remind you of. So the two x coordinates are -1 and -3. If you add them and divide by 2, you get -2. The y coordinates are 5 and -1. If you add them and divide by 2, you get 2. So -2, 2, that is the midpoint of the segment PT. I wanted you to plot that. And then you can do the same thing for the midpoint of the segment from Q to R. So Q's x-coordinate is 6. R's x-coordinate is 10. So 6 plus 10 divided by 2 is 8. And the y-coordinates, Q's y-coordinate is 5. R's y-coordinate is -1. So 5 plus -1, that's 4. 4 divided by 2 is 2. So 8, 2, that's the midpoint of QR. And if you connect those two midpoints together, you get something called the mid-segment. I wanted you to see, notice in this figure, it's a horizontal line, so it's also parallel to the two bases of the trapezoid. But there's a simple relationship between the lengths. So I had asked you to count the length of PQ. Literally, if you count the spaces, that PQ is 7 units long. And if you count the spaces, TR is 13 units long. But the mid-segment is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spaces long if you count the spaces. And what I wanted you to see is there's a relationship between the mid-segment and the lengths of the bases, the 7 units and the 13 units. So I said that the length of the mid-segment is halfway between the 7 and the 13. So notice between 7 and 13, halfway between them is 10. So another way to think about that is averaging the base lengths. So if you take the 7 and the 13, if you add 7 plus 13, you get 20. And if you take that and divide by 2, you get 10. You get the length of the mid-segment. The mid-segment connects the midpoints. It is in the interior of the trapezoid, and its length is just the average of the bases. Just like we average the x and the y coordinates to find the midpoints coordinates, to find the length of the mid-segment in a trapezoid, you just average the lengths of the bases. So for isosceles trapezoids, so again, isosceles trapezoids on our final exam study guide are right here. They're a special kind of trapezoid. But just like isosceles triangles have congruent legs, isosceles trapezoids also have congruent legs. So these are the bases, the parallel sides. So the congruent legs are here, AB and CD. Those are the legs. So just like an isosceles triangle, if you have an isosceles triangle, what that tells you is that the base angles are congruent. Well, same thing. If you have an isosceles trapezoid, here's our isosceles trapezoid, angles 1 and 4, I numbered them. Those are angles A and D. Those have to be congruent. So here's the proof, and I want you to see that it uses a combination of all kinds of things that we've talked about over the course of the trimester. And I'm telling you, this is a challenging proof, so it's okay to have struggled a little bit on this one. So I copied in the given. So knowing that you have an isosceles trapezoid, that tells you not only that BC and AD are parallel, those are the bases, but it tells you that BA and CD, it tells you that the legs are congruent, and that's simply what we mean by an isosceles trapezoid. An isosceles trapezoid is defined as having congruent legs. It's a trapezoid with congruent legs. Now, notice, now I claim suddenly that ABCE here is a parallelogram inside of this isosceles trapezoid. Now, notice, it's a parallelogram because in the given, I was told that AB and CE are parallel, but notice because of the trapezoid, the BC and here this segment are already parallel. So I know I have a parallelogram because the opposite sides are parallel. So, and now I'm going to use a parallelogram property. The CE and the BA, those are opposite sides in the parallelogram. So a parallelogram gives me opposite sides that are congruent. And now we're going to use the transitive property. I know that CD right here is the same as BA, and BA is the same as CE. So I can connect those together and say that segments CE and CD are congruent. So that's the transitive property. But look at what CE and CD are. Those are the legs in this triangle. So that triangle is now isosceles. So notice here, if I know that CE and CD, if I know that those are parallel, or rather are congruent, I can use that property in just a moment. Now, first of all, I want to focus on angles 1 and 2. Those are in the parallelogram. Notice that those are opposite angles. So in a parallelogram, there's one of our properties. I know the opposite angles are congruent. So here, 2 and 3, look at this. Parallel lines, 2 and 3 are alternate interior angles. So I know 2 and 3 are congruent because parallel lines give me alternate interior angles that are congruent. Now in the figure, I also know 3 and 4 are congruent because of this isosceles triangle. So congruent legs give me congruent base angles. So notice 3 different relationships from 3 different chapters. This is the quadrilaterals unit, this is the parallel lines unit, and this is the unit about triangles and congruent triangles. But it gives us 3 different angle relationships that we can connect together in order to get to our proof statement. This is one giant, like a train, if you will. That's why at some level, I like to think of that analogy as the transitive property. Look, we can connect angle 1 to 2, but 2 is connected to 3, and 3 is connected to 4. So we can connect 1 directly to 4 using the transitive property. And that was what we wanted to show, that angles 1 and 4 have to be congruent in the isosceles trapezoid. So the reason that it's good to look at a proof like this today, I'm not going to expect you to be able to do a proof that complicated, but this idea of connecting angle relationships together and using the transitive property at the end is exactly what you need to do on proofs 3 and 4 on the review guide for the final exam. You are using angle relationships and connecting them together with the transitive property in order to get to your proof statement. So the last proof then is another property of isosceles trapezoids. The diagonals are congruent. So if I start with FGHJ being an isosceles trapezoid, what I want you to see here is I actually can split it apart into 2 triangles. So I can think separately about the triangle GFJ, which I drew over here, and then I can also think separately about the triangle FHJ. I drew that triangle over here on the right side. So I want to mark everything carefully. I'm starting with an isosceles trapezoid. That's our given. But remember, if it's an isosceles trapezoid, then that means that I can mark that the legs are congruent. So I can mark that GF and HJ are congruent, but then I also mark the GF and the HJ in my separate triangles. Isosceles trapezoids, those are trapezoids with congruent legs. So next, I know isosceles trapezoids also have congruent base angles. We just showed that in the proof above. So I can say that the angle GFJ, the big angle here at this vertex, is the same as HJF, the big angle at this vertex here. But those angles in the separate triangles are this angle at F and this angle at J. And then notice in the main figure, by the reflexive property, FJ is congruent to itself. That side is shared by the two triangles. So literally, I can mark FJ in the triangle on the left and in the triangle on the right. But now we have congruent triangles by side angle side. So I can say that GJF is congruent here, GJF, and I wrote it wrong here. Notice triangle GJF has to be congruent to triangle HFJ, so I wrote it in the wrong order. That's by side angle side, and the order is important because now we're going to use the triangles that are congruent to say we have congruent parts. So now GJ is congruent to HF. GJ and HF are the diagonals. So look, the way I wrote it is important. GJ are first and second in the name of the triangle, so are H and F, first and second in the name of the triangle. Once the triangles are congruent, then their corresponding parts are congruent. That's Cpctc. And the reason that I wanted to look at this today is because on your final exam review, the last two proofs that I wanted to consider, proofs 5 and 6 that I'd like you to try for tomorrow, those proofs both end with making parts that are congruent. So you'll have to use Cpctc at the end of this proof. But what that means is in the step before it, in both of these proofs, first you have to make congruent triangles using one of the methods that we studied in Chapter 4.